So far what we have seen is that we have seen a result which shows that in Byzantine agreement problem, if we have 1/3 of the generals are faulty, then Byzantine agreement is not possible. Now, otherwise we still have to look at algorithms which can achieve Byzantine agreement. So, we will start with a classical algorithm which was designed by Lamport, Shostak and Pease. So, this is the classical algorithm for Byzantine agreement, and then thereafter we will look at algorithms which trade off the number of messages. This algorithm requires a huge number of messages. We will trade off the number of messages with the resilience and other things. So, the algorithm will be presented recursively, and the core algorithm is broadcast n comma t, where n is the number of processes which are participating in the agreement protocol and t is the resilience. So, t, remember, is a parameter of the algorithm, alright, and we will show that the algorithm will succeed only if the number of faulty generals is less than t. Okay, so, but a priori we do not know that how many of the generals are faulty. So, the algorithm is run with the parameter t. Now, is that clear? The t is a parameter of the algorithm which we choose at the beginning, right. It is not something which has any bearings as such on the number of faults. It is not the number of faults, it is a parameter, right. With that understanding, we first look at the code for broadcast n with 0, okay, and t is also going to reflect the number of rounds that we are going to have. So, we are going to have t plus 1 rounds of the protocol every time. So, broadcast n t will require t plus 1 rounds of the protocol, broadcast n 0 will therefore require only 1 round of the protocol. And what do we do in that round? The general sends the value xj, xg, the value of the general, to all processes, and the lieutenants do not send anything. And then everyone receive messages of pulse 1, the general decides on xg, and the lieutenants decide as follows, that if a message value x was received from g in pulse 1, then decide on x, otherwise if it does not get a message, then it will decide on undefined udef. Okay. This is the code for broadcast n 0, that is when the protocol is run with n as the number of processes and the value of parameter t as 0. Is that clear? Now, we will look at broadcast n t, and that broadcast n t will be defined recursively, and the base condition for that recursion is broadcast n 0 eventually. Is that clear? It is a slightly tricky algorithm. So, let us go slowly through the algorithm and it will be clear. So, we are looking at broadcast n t now, and this protocol broadcast n t will go through t plus 1 rounds. Okay. In the first round, this is what happens. The general sends xg to all processes, the lieutenants do not send. So, in the first round, it is only the general which transmits its value to all the other processes. Receive messages of pulse 1, okay, they all receive messages. Now, what do the lieutenants do? So, let us consider lieutenant P. What does lieutenant P do? If it receives a message from G in pulse 1, okay, then it sets xp to equal to x if the value x was received here, otherwise xp is set to undefined. Okay. And then it starts its version of broadcast n minus 1 t 1 minus 1 in the next pulse. Okay. All right. So, let us look at the scenario here. The general G in the first round, the general G starts broadcast n t. How does it start that? It sends its value x to the lieutenants, right. What does a lieutenant P do here? When it receives the value x, it starts its version of broadcast n minus 1 t minus 1. Whose version of broadcast is this? P's version. So, we say broadcast P. Okay. Why n minus 1? Because it starts this among all the processes except G. So, n minus 1, right, and the parameter t minus 1 is t is reduced to t minus 1 because this is a recursive call, and this is the one which is going to decrease and at some point it will reach 0, and then the previous slide will apply, the slide on which we talked about broadcast n0 will apply, right. Now, see, just like P started a broadcast P n minus 1 t minus 1, Q, which is another lieutenant, in the same round will start broadcast Q with n minus 1 t minus 1. Now, these two, namely this broadcast n minus 1 t minus 1 and broadcast n minus p n minus 1 t minus 1, these will start from the second round, right. In the first round, G starts broadcast n t and sends its value to all the processes. In the second round, P will start broadcast P n minus 1 t minus 1, Q will start broadcast Q n minus 1 t minus 1. So, what are these broadcasts doing? Intuitively, what this means is that here P tries to tell others that G told me that its value is x, right, and Q also starts that, telling others that G told me that its value is x, right. Okay. Now, note that G can be loyal or disloyal, right. If G is disloyal, then broadcast P is sending out one kind of value, broadcast Q may be sending out another kind of value, because G may have told them two different things. To P it told some value of x, and to Q it told some value of x hat, if G is disloyal. Okay. Now, they are trying to arrive at consensus among themselves, keeping G out, about what G had said, right. Yes. Oh, yes. That's I have not mentioned that explicitly, but obviously when broadcast P starts this thing, it will send it out to everybody except G, right. So,
case in which there might be a false initiator and a true initiator also the same thing.
no. See, the senders of messages are always known, right? And this protocol by definition starts with one initiator.
Because but if what stops on a false or a faulty, like one true person has started a wave initiate, but what stops a normal this from starting?
Faulty one can also start that, but that will be treated as a separate instance of the protocol. You know the initiator of the protocol, so that will be treated as a separate instance, separate run. Those messages and these messages will not get interleaved, in the sense that they will not, you will keep them separate. Each process will keep them separate, right? Okay. Now, what will happen in round 1, in round 2? In round 2, P will start this, right. So, what will P do? P will broadcast the value of x which it received from G to the other processes. What will a process Z do here when it gets this? It will start its version of broadcast Z n minus 2 t minus 2 among those processes, all processes except G and P, right. Okay. Now, note that Z, when it gets a message from Q corresponding to this protocol, this instance, for this Z will also start broadcast Z n minus 2 t minus 2, but this broadcast will work on all generals except G and Q. This broadcast includes everyone except G and P, this broadcast includes everybody except G and Q, right. Now, this is how recursively this will start. And can you tell me in which round all of these are going to terminate? In the round t plus 1. Why? Because you see, the one which starts in round 1 with t, if that ends in t plus 1, then the one which starts in round 2 with t minus 1 will also end up in the round t plus 1, and the one which starts in round 3 with t minus 2 will also end up in round n plus t plus 1, right, because whenever t becomes 0, then this thing that we broadcast n0 will apply. Okay. All right. Now, let us proceed to the next thing. So, what happens in pulse t plus 1? In pulse t plus 1, receive messages of pulse t plus 1, the general decides on xg, general always decides on its own value. Okay, that is mandatory, because if the general is loyal, then it is mandatory that the general's value is the agreed value. So, the general itself will also have to agree to that value. And for lieutenant P, in the round t plus 1, some decision on broadcast q n minus 1 t minus 1 will have occurred, okay, recursively, okay, and let WPQ be that decision. Now, just like broadcast q had a decision, broadcast P, broadcast Z, broadcast M, all of them will have a decision. So, we take the max of those decisions to give the decision for YP. Okay. Actually, there is this is a slightly okay. Just let me correct this. This max is confusing. What I mean actually is that it should be majority. Now, let us understand this once again. The protocol started by with G started executing broadcast N T. Okay. It started by G sending out its value to all processes. So, let us say P, Q, R, right. This is what happens in round 1. Okay. In round 2, P will start broadcast P n minus 1 t minus 1, Q will start broadcast Q n minus 1 t minus 1, and R will start similarly broadcast R with the same parameters, right. Now, after in the round k plus 1, okay, this is round k plus 1. See, this will reach some decision recursively, right. This agreement will reach some decision. Now, look at process P. Process P is participating in this broadcast. In fact, this is the initiator for this broadcast. So, process P will have an array, and this array will have entries for P, for Q, for R. The decision that P reaches on the outcome of this agreement protocol will be stored here. Now, see, P also participates in broadcast Q, this broadcast. Why? Because Q is going to send it to everyone except G. So, in this broadcast Q, P is one of the lieutenants. So, at the end of this, P will have some agreed value for the value that Q had sent. Okay. So, that value, P's value of the agreement of this protocol will be stored here. Similarly, P participates in the broadcast initiated by R, and therefore, when this protocol terminates, P will have some value corresponding to this broadcast. That value is put here, right.
P cannot know what value Q decided finally.
No, it does not, but if the agreement succeeds,
yes, but that may not be the value which P had.
may not be. So, let us understand what do these values represent. This value represents the value that P thinks G sent it, right, and that value will be the value that G had sent it. Why? Because it got it directly from G, and this was the initiator of broadcast P. So, it will always agree, it will always have the value X which G had sent it, right, unless of course P itself is disloyal, right. What is this value at P? This is the value that P thinks G told Q. What is this protocol? This protocol is where P, Q, R are trying to decide or agree upon the value that G apparently had told Q. Okay? Now remember that G may be malicious, Q may be malicious, but the non-malicious generals will have to agree on the value which Q had broadcast in broadcast Q n minus 1 T minus 1.
He stored the value x which got from G or which broadcasted?
No, Q started this broadcast Q. Okay? It started this. So, PQR, if this protocol succeeds, PQR will agree, all the loyal generals will agree on some common value. That value is this. Okay? Even P knows that value.
Whichever value Q was broadcasted, that would be the value stored here.
It could be that value or it could be some other value also. If Q was loyal, then it has to be that value. And if Q is disloyal, then it can be any value, but that value will be agreed upon all the loyal generals.
But whatever if Q has broadcasted that time, that will be the same value which is stored here, or could it change?
If Q is disloyal, then it could be some other value.
But any value which he is finally broadcasting, if he is disloyal, he could have broadcasted any other value also.
No, not it may not be that value.
It may send different values to different.
Yeah, it will send different values to different. If it is disloyal, that's what it will do. See, this in its own right, is a Byzantine agreement protocol, right? This in its own right is a Byzantine agreement protocol. This in its own right is a Byzantine agreement protocol. Each of these will reach separate agreements. What will this result in? It will result in all the loyal processes agreeing on a common value for this protocol. This likewise will result in everybody agreeing on a common value for this one. Now, the values agreed upon for this and the value agreed upon for this, they are stored in separate elements of this array.
This is P.
In P. Similarly, Q will have such an array, R will have such an array.
How does P come to know what is decided by Q?
No, you are not getting the point. See, the broadcast Q is a protocol which is started by Q. Corresponding to that protocol, P will have some agreed value. That is what is stored here.
Sir, one point.
Yes.
Q has send its value which is received from G to another, let's say another node called Z. Now Z will again send this value to P.
No, forget about the subsequent round.
So I am asking the subsequent round.
No, forget about the subsequent round. First understand this thing. Assume that this protocol is a black box. This protocol is a black box in T rounds from here. It will reach some agreement about the value that P had broadcast. Right? Let us assume that that will happen. That this broadcast will cause every process except G, which is not participating in this protocol, every process except G will agree on the value that P is sending. If P is loyal, they will all agree on the same value. If P is disloyal, the loyal generals will still agree on some value, but that may not be the value sent by P. That is what is the outcome of broadcast P n minus 1 T minus 1, right? And every process will store that outcome in its own array at the pth position, right? Similarly, everybody will store the outcome of this one in the qth position of their respective arrays, right? Okay. So, each of them is going to have this array, right, and they will put in those values in those, right, and then they will take the majority among these, they will take the majority value out of this. Now, without loss of generality, suppose the values being transmitted are 0 or 1. So, majority means whether you have more ones or more zeros, that is the value that you will put in here, that is the value that finally P will accept at the round t, at the round t plus 1, this is round t plus 1, at the round t plus 1 they will, P will take the majority of these, and that will become the final value of P, right. This is the recursive definition of the algorithm.
So P will also send the message to Q, which will send it, Q may send a message to R in that thing, and R will again send it to P in some other time, then third in the subsequent round. Then we have got two messages from R to P.
But they are separate sub instances of the protocol.
Yes. So for every instance, do we maintain a vector?
Every round.
You see now, let's see, we are consciously trying to avoid flattening the thing out, because then it will become very complicated. The thing that you have to understand here is that when this broadcast is taking place, a process P will start its own version of broadcast. Okay, it will start its own version of broadcast, which is broadcast P with n minus 1 t minus 1. The set of processes participating in this broadcast, whatever takes place here, the set of processes participating in this is the original set of processes minus G, right. Now, in this protocol, within this protocol, again recursively similar types of things will happen, right, but all these messages that are part of this broadcast protocol will be treated separately, the data structures will be treated separately. So, for this protocol also the set of processes will need that array, but that array is not this array. This array is separate from the array that broadcast P n minus 1 t minus 1 will require for its execution. So, it is, please try to consciously think of this as a separate run of the protocol, which has no overlap neither in terms of the messages nor in terms of the data structures with the execution of this broadcast. I mean this broadcast that you start, that G started here, okay, with NT, this just recursively starts this protocol here. Similarly, it recursively starts a copy of that protocol called broadcast Q n minus 1 t minus 1, right. But these copies you treat them as completely separate executions of the protocol, which does not have any messages or data structures in common with the execution of this whole thing. Think of these protocols executing in isolation as a completely separate instance. All that we are interested to know is that the outcome of this protocol is that every process in the pth entry. So, for Q this is the this thing, in P there will be a simple similar entry for P, and in R also there will be a entry corresponding to P. All we know is that when this terminates successfully, all generals, loyal generals will have the same value of x, the x that P started the protocol with. right, and that agreed upon value is stored in the entry corresponding to P in each of these processes, right. Similarly, independently Q had started broadcast Q with n minus 1 t minus 1. This broadcast is another independent execution of this protocol, and the outcome of that is in each process at the qth location they will all agree on some common value y, the loyal ones, right. Okay. So, what is going to be the size of these arrays in all of these? N minus 1, and out of those n minus 1 you will take the majority value, and that will be the value that Q decides in broadcast NT. Okay.
So there will be another n minus 2 broadcast P n minus 2 t minus 2 protocols running.
They are fully contained inside these. Those are fully contained inside the recursive definition of broadcast n minus 1 t minus 1.
No, I am talking about Q will send a message to P, and we will have another broadcast P n minus 2 t minus 2.
Yes,
running.
but that broadcast is fully contained inside this one. It is fully contained inside this one. You don't try to get into that. Don't try to flatten out the algorithm, then you will have too many executions of similar types of things. Remember that they are separate executions of the protocol, so they are not going to get mixed up with this. The messages for this execution will not get mixed up with the messages of this execution. They are totally separate executions.
What is the decision criteria?
Hmm?
What is the decision criteria, that is, if you are receiving values again and again, let's say P has
So, the decision criteria here is that if finally in the round t plus 1 the outcomes of broadcast Q, broadcast P, broadcast R are all already there. So, you then take them, each one of them takes the majority of that, and that becomes the decision for Q in broadcast NT, that becomes the decision of P in broadcast NT, and so on.
individual broadcast, how will I decide? Individual one, because let's say the value of inside Q, the value of P variable, it will get multiple values, when you get different values.
Why will it get multiple values? Corresponding to this execution of this protocol,
You have to take the Q.
there will be a single value y that Q will decide on.
You will keep getting, yes, inside of one, but keep getting messages again and again. So,
Why will it keep getting messages again and again? Think of this as a procedure.
because if it goes,
Think of this as a procedure at the end of which each one of them have one decision for the value that was broadcast here, and that decision is y. Don't get inside this thing. Treat this as a black box execution of the protocol. Recursively inside it will do a lot of things, in fact the same things, but never try to interfere the messages here and the messages here, then you will get thoroughly confused. Think of this as a completely separate execution. Hmm? Yeah?
Think of each box as
Yeah, think of them as happening totally in isolation, right? Otherwise, the common problem that happens is when you try to flatten out the execution of the algorithm, then it is very hard to intuitively capture what is happening, but that is not what you should do. It is a very nice recursive formulation, so keep it recursive, right? That is what we have to do. Okay, so is the algorithm roughly clear what is happening, right? Now, keeping the recursive flavor in mind, we will prove the correctness of the algorithm. Okay. Now, to prove the correctness of the algorithm, let us first start with this result. We first prove termination. Now, termination is obvious, there is no the only thing that we need to see is that where does the recursion terminate. So, in every recursive call t is decremented. So, somewhere down the line t will become 0, okay, and at that time this will apply, right, broadcast n0 will apply, and broadcast n0 has no problems in termination, it terminates in round 1, right, okay. And another thing is that always n is greater than t. So, in all the recursive calls when you do n minus 1 t minus 1, n will never reach 0 before t, right. It can never be the case that n has become 0 and t is still positive, that will never happen, because in all the recursive calls we are just decrementing both parameters. So, if n is greater than t, then n minus 1 will always be greater than t minus 1, right. So, that is all that we need to see for termination, right. Now, we will look at two results. So, we will first start with this lemma and then come to the actual proof. This is for the correctness, okay. So, what we will first show is that if the general is correct, if there are f faulty processes and if n, the number of processes, is greater than 2f plus t, then all correct processes decide on the input of the general. Okay. Now, to do this we will again use induction to prove this. So, for the proof, first look at broadcast n0. If the general is correct, what will happen? It will broadcast the correct value to all the processes, and all the loyal processes will simply accept that value. Okay. Just remember just look at the code of broadcast n0. The general sends its value to all processes, and the lieutenants, if they receive the value, they decide on x. Okay. So, for broadcast n0, it is obvious that the algorithm will terminate with the proper value. Now suppose for induction, assume that the lemma holds for the recursive call broadcast So, what does the lemma say? The lemma says that if the general is correct and if n is greater than or equal to 2f plus t, then all correct processes decide on the input of the general, right. Now, if n is greater than 2f plus t, okay, we are given that n is greater than 2f plus t. So, if n is greater than 2f plus t, then this implies that n minus 1 is greater than 2f plus t minus 1, right. So, if in the for the entire set of processes, if this holds, then this also holds, right. So, for your broadcast n minus 1 t minus 1, this condition, this necessary condition is still satisfied in your recursive calls, right. And however, these broadcasts that are done, they may be done by not necessarily the loyal generals, because see what happens in the first round, G is going to broadcast its value and they will all start this broadcast n minus 1 t minus 1. Now, not all of them are loyal. So, the loyals one, what will the loyal ones do? What will the loyal ones do? They will get the value of G and start broadcast n minus 1 t minus 1 with the same value of that it received from G, right. So, all the loyal generals, all the loyal lieutenants, they will start broadcast n minus 1 t minus 1 with the same value, right. They will all start broadcast n minus 1 t minus 1 with the same value, and by the induction hypothesis they will all succeed. That means that in your final array, at each process corresponding to the loyal generals P, Q and R, you will have the same value x, right, in each of the processes, all right. And if these are in the majority, then the majority value will be x only, right. Okay. Now, if n is greater than 2f plus t, then obviously the loyal generals are in majority. So, this result holds, this lemma is proved. Is that understood, or should I repeat? Repeat. Well, see, firstly what we have shown is that how does the protocol work? It starts by executing the G starts by executing broadcast n t, right. When a loyal general, so we are saying we are given that G is loyal, we are given that G is loyal. When a loyal general P receives this, what will it start? It will start broadcast P n minus 1 t minus 1, and what value will it start with? It will start with x only, because this is a loyal general, it has sent a value x to the loyal general, and the loyal general will start with that only to do this. Now, we observe that if n is greater than 2f plus t, then n minus 1 is also greater than 2f plus t minus 1, right. Now, look at this broadcast, it is started by a loyal general and this is satisfied that. So, by the hypothesis, induction hypothesis of this, we assume that this broadcast will be successfully satisfy this property that all correct processes decide on the input of the general, right. But what does that mean? It means that in the last round, remember that P is accumulating an array, Q is accumulating an array, and what are they what does this guarantee? This guarantees that the value that was broadcast here, namely x, is going to be the agreed value among all loyal generals. So, P will have x here, Q will have x here, R will have x here, okay, in the same place. Okay. Similarly, for another loyal general, let us say Z, in the zth position also we will have x, okay. In the zth position also we will have x, the zth position also we will have x. So, in the last round, for every loyal general in these arrays we have the same values, right. And then if the loyal generals are in majority, then the majority values picked from these arrays will become the same. So, we will have agreement, right. Now, what is the case that is remaining? That if the first general, the general which initiates it, if that is not loyal, right, if that is not loyal. So, if the initiator is not loyal, then look at this thing. Suppose G is not loyal, right, it starts broadcast n minus 1 sorry n t. Now, when P starts this, right. Now, what did we have here? The guarantee here was T is less than n by 3, okay. Okay. The result that we are trying to prove is that all correct processes will decide on the same value, all right. Now, if T is less than n by 3, okay. Now, at this point, if there are f faulty processes, how many faulty processes are there in broadcast n minus 1 t minus 1? So, here the number of faulty processes has gone down. Now, note one thing, that if here among n processes you had less than 1/3 faulty, then here among n minus 1 processes you will still have less than 1/3 faulty, because G is one of the faulty ones. So, you had f out of n. So, f out of n, now you have f minus 1 out of n minus 1, right. So, if this is less than 1/3, this will also be less than 1/3, fairly simple to verify that, right, all right. And t less than n by 3 implies t minus 1 is less than n minus 1 by 3, right. Okay. Now, all the correct lieutenants, what are they going to do? All the correct lieutenants, what will they do? They will whatever they have got, and by the previous lemma they will all reach the same value at the end. So, now think of the arrays corresponding to all the processes in the round t plus 1. Corresponding to the loyal lieutenants, we will have identical values, but the value corresponding to loyal lieutenant x and the value corresponding to loyal lieutenant Y may not be the same, because G sent some value to X and some other value to Y, right. So, their respective broadcast started with two different values, but in the end all the loyal processes will have the same value for the value that was broadcast by X and the same value for what was broadcast by Y, right. What is going to happen for the non-faulty ones, for the faulty ones? Now, look at this thing. All the, if we look at two of the arrays, the array for P and the array for Q, okay. If you look at the positions corresponding to the loyal ones, you will see that they will have identical values, right. Now, if we take majority of this, are we going to agree on the majority? How many good ones do we have? More than 2/3. May not be. Some of them are saying 0, some of them are saying 1. But all of them, their arrays are identical. Right? So, can it be possible that the majority here and the majority here is different? Yeah, that is what I am asking you. See, they can differ in, these arrays can differ in at most less than n by 3 positions. In all the other positions, they are exactly identical. So, if we take the majority, then is it possible that we will have different values? Here?
Can differ.
Can?
They have to come from lower side and again they are taking majority.
It can differ because it depends on how many zeros and ones are there and how many faulty zeros and ones.
Okay, we will discuss this in the next class. Think about it and let me know. So, but is the final step clear? What we have arrived at is that initially the general broadcasts some value. If the general is disloyal, it can send different values to different people. They will start their copies of broadcast n-1, t-1, and that will result that for all the loyal generals, we are going to have exactly the same agreement for each of these different sub protocols, right? And then they take majority. Question is, do they reach agreement or not? We will take that in the next.